There are many things in life that we take for granted and help human convenience. For example, cars, planes, our phones, the internet, all of these things. But there's been one that has been especially a hot topic recently, and that is toilet paper. This is one of the tamer fights that have happened over toilet paper. Now, I know this might seem like a first world problem, but the lack of toilet paper is a serious thing, and I agree. Toilet paper is just so soft, and, well, I just can't imagine living without it. So, that brings me to my idea. I want to know more about toilet paper.
Well, what do you mean by that?
Well, I want to use physics to figure out more about toilet paper. Specifically, I want to figure out the moment of inertia of this toilet paper roll without using mass.
How exactly are you going to find the moment of inertia without using mass?
My voice. I'm glad you asked, Interme. First, I'm gonna let the toilet paper roll down a ramp with the height of one tape roll. Then I'll let the toilet paper roll down a ramp with the height of one toilet paper roll. And then I'll let the toilet paper roll down the height of a ramp with one tape roll and one toilet paper roll combined. Then I'll let the toilet paper roll down the height of a ramp that is two toilet paper rolls, and I'll finish by letting the toilet paper roll down the ramp with the height of two toilet paper rolls and one tape roll. I will roll the toilet paper down each ramp 3 times and measure the velocity of the toilet paper roll at the very end. I will then average each different trial's final velocity for each height. I'm also going to measure the height of each of the 5 different heights. By measuring the heights of each of the different heights, I can calculate the kinetic energy in the system. Oh yeah, by the way, I'm going to use this equation to figure out the moment of inertia, hopefully without using mass. If we arrange this equation a little bit, we get this equation. By looking at this final equation, we can see that if we choose a different kinetic energy, the ending velocity will change. The kinetic energy is equal to the gravitational potential energy, so the height is what directly changes the kinetic energy. The independent variable in this experiment is the height of the ramp that the toilet paper is dropped from, and thus the dependent variable is the ending velocity. Then we plot 2k r squared on the y-axis and v squared on the x-axis. The linear slope should hopefully be the real moment of inertia, and the y-intercept should hopefully be mr squared.
Well, how are you going to measure the kinetic energy and the velocity?
Velocity is the easy part, but first I'm going to let the toilet paper finish rolling on the ramp and measure the time it takes for the toilet paper roll to roll a certain distance, in this case let's say 5 centimeters. Kinetic energy is the hard part. Because we know E naught equals E final, then we can determine the starting gravitational potential energy is equal to the ending kinetic energy. So basically we can substitute K for UG. Calculating UG is easy, just do mgy. Okay, well, we're already too deep in this project. Let's just say that we happen to get a scale. Sorry, the scale turned on. It's in grams mode, and this is the one I rolled. Let's check, 169 grams. But we don't know the inner radius of the toilet paper roll.
I see what you're doing now. Because you don't have the inner radius of the annular cylinder, that means you won't be able to directly calculate the moment of inertia of the toilet paper roll.
Exactly. See, this experiment still can work. Well, there's nothing left to do except for do the trials. Right, hello, this is me. Try number 6. So in hopes of getting a better, more accurate time, I'm using my dad's phone to record and Apple phone to time, because I realized Apple can go to hundredths of a second, while this phone, this specific one, only goes to tenths of a second. Kind of unfortunate, but I guess that's how we're gonna do it. So this is the ramp. This is the run course, I guess. After the toilet paper, this toilet paper has rolled down the ramp. I'm not doing 5 centimeters because I realized I'm not a god timer. Not 15 because I realized I'm still not a god timer. We're gonna try 30, see how it goes. This is the height, and I measure the height. Oh, I'm writing my notes here. Height 1, 10.5 centimeters. I'm gonna write my 3 velocities here, find the average, and do that same thing for height 2. Measure the height, 3 velocities, find the average. Yeah, you get the point. Okay, let me set this up. Okay. Alright. Height 1, trial 1, begin. 0.36. Oh, 0.36. That's our first time for our first trial. Okay, so this is my original data that I took my notes from. It's kind of messy with its slash marks and some crossed out letters, so I decided to rewrite the data, and this is the rewritten data. So as you can see here, these are our first steps on our calculations. So for each different height, we took 3 times it took for the toilet paper roll to roll 30 centimeters, and then we averaged them to get the average time it took for the toilet paper roll to roll 30 centimeters. And then we did the distance that it traveled, so 30 centimeters divided by the time it took to get meters per second, which is also the final velocity. Wow, that's a lot of calculations. Okay, let me run through them step by step. So the first step, we have E naught equals EF, and then we translate that to UG equals KE, because all the potential energy in the initial is translated into kinetic energy in the very end, and then we substitute mg to mgy, or ug to mgy, and then we can calculate the kinetic energy for all the different heights, and we just substitute, but the only thing that changes in all of these calculations is the y. So, and then the y changes because that's different heights, and then we calculate in the final step the kinetic energy for all of them. So what we do from there is we take the KE that we got and we plug it into 2k r squared for the y-axis, and we do this for all the 5 heights. Oh, just so you know, the units for 2k r squared is J for joules. So we found our numerator part of the equation. Now we need to find the denominator part. All we have to do now is take the velocities we found here and square them. Okay, so we found the numerator part, the denominator part. Now we need to find the y-intercept part. This is also quite easy. All you have to do is plug in mr squared, and that's it. Oh yeah, by the way, the outer radius of this toilet paper roll is 6 centimeters, as I measured here. I first measured the diameter, which is 12 centimeters, divided in half, 6 centimeters. Now that we have this information, all we have to do is put this information on a data table. How do you put it on a data table, you ask? Well, first you have to put v squared on the x column, in the x column, and 2k r squared on the y column, and that's it. So then we make the corresponding graph, and hopefully the slope is the real moment of inertia, and the y-intercept is mr squared. Wait, hold up.
The prophecy is true.
Okay. So our predicted y-intercept is actually really close to the experimental y-intercept here. So we might be onto something.
But there's a negative sign in this equation, so in fact you are more than really wrong.
First of all, you're wrong. Second of all, you're wrong. Third of all, if what you're saying is correct, that means at one point in time, there's going to be a negative energy in the system, which doesn't make sense. How do you have whatever. Fourth of all, the negative sign here doesn't mean that the y-intercept is actually negative. The negative sign here means that there is a y-intercept. It means that from 0 to a point, there's a difference, which is a y-intercept, not negative. So now we have the slope of our graph, which hopefully is the moment of inertia. Now all we need to do is calculate the actual moment of inertia, and then we can compare. We can find the percent error for both the y-intercept and the slope. We can calculate the real moment of inertia using this equation. M represents the mass, R1 represents the inner radius, R2 represents the outer radius. Oh, by the way, I measured the radius of the inner circle of the toilet paper roll by first measuring the diameter, which was 4.25 centimeters, and then in radius, that's 4.25 centimeters divided by 2, or 2.125 centimeters. By plugging in the numbers, we see that the real moment of inertia of this toilet paper roll is equal to 0.000342 kilograms meters squared. So comparing this back to our graph, Okay, let's take a step back and let's look at this graph one more time. So what can we see from this graph? Well, on our y-axis, we have 2k r squared with the units joules per meters squared, because joules as in kinetic energy, meters squared because radius is measured in meters. On our x-axis we have velocity squared, and that's measured in, well, velocity is meters over seconds, so velocity squared is meters squared over seconds squared. Our slope is linear, which is good, it should be linear, and our y-intercept is pretty close to what actually the real y-intercept is. And this is without having to linearize the graph. Like when I plotted my data points, the graph automatically came out. So thus, it can be concluded that as you linearly increase, or as you directly increase the height, then also the velocity changes at a direct rate, not square rooted. As one increases, the other will increase by proportion as well. Now all we need to do, hopefully, is calculate the percent error for our y-intercept.
Nice.
Okay, so looking at the y-intercept, I realized I didn't do as bad as I thought, which is always good, you know? I'm actually pretty happy with this. Some potential sources of error that might have come out throughout the whole experiment are the fact that toilet paper rolls, when they roll, they make sound, and that's, even though E naught equals E final, there's some loss of energy due to sound, heat transfers, blah blah blah. But also, I'm not a god timer. I can't time to the hundredth of a second perfectly every single time. So yeah, also, we unfortunately don't live in a perfect physics world. I wish. Maybe in the perfect physics world where armadillos are perfectly spherical, Kyle's cars are perfectly aerodynamic, and rivers flow at an exact rate without any bumps, maybe then we could have gotten some more accurate measurements. But alas, we are here in the physical world where I only have a ruler to measure distance and my phone stopwatch without a god timer in my hand. There could have been some ways that I could have improved my accuracy. For example, do more trials for each height so that the average velocity is actually correct, or more correct than it is. Do more heights so that in fact there are more points on the graph so that each point doesn't weigh as much to the final answer. Maybe I could have gotten some more sleep so my reaction time would have been better, but yeah, these are things that might have happened. Okay, so if you want to know how I came up with this idea of finding the moment of inertia of toilet paper, well, first I thought that if I wanted to make a video, it would be based on toilet paper because first of all, it's a joke, and it's kind of a cry for help. It's a joke because the first thing people go to grab in stores when like an outbreak comes out is toilet paper, but like, okay, whatever. Anyways, the second part is like, it's a cry for help because, well, for 2 weeks now, this house has only had 7 to 8 rolls left. All the rolls that I used in the video were all the rolls of toilet paper we had, and yeah, it's kind of scary. But now I guess it's better because you can go buy toilet paper now. It's not fully stocked out. Yeah, it was just kind of a random thought that I want to do something in toilet paper, and I guess we're rolling toilet paper. So we're just going to roll the toilet paper down these different heights, like so, and yeah, hopefully that's it. Wait, Mr. Hires, I really need to get this back to you.